So, hello everybody, this is Dr. Ritu Singh from Basic Science Department, and today's topic of discussion is Raman spectra. This is the last spectra of Unit 2. Before this we have done UV visible spectra, then IR spectra and rotational spectra. So, the fourth one is Raman spectra. Now, Raman spectra is different from other spectras which we have discussed, because if we consider UV, IR or rotational spectra. In case of UV spectra, we were dealing with ultraviolet, absorption of ultraviolet radiations. In case of IR spectra, we dealt with absorption of infrared radiation. In case of rotational spectra, we dealt with absorption of microwave radiation. So, in all the three spectras we were dealing with radiation, but we were dealing with absorption of radiation. But in case of Raman, we are not going to deal with absorption of radiation, we are going to deal with scattering of light or scattering of radiation. So, Raman spectra basically deals with scattering of radiation. Scattering of light. Now, all the spectras, all the four spectras, they have got some dissimilarities and they are having some similarities also. So, at the end I am going to discuss all the four spectras, what are the similarities, what are the dissimilarities, but first starting Raman spectra. In Raman spectra, the radiation which is used is going to lie it lies in ultraviolet or UV range. So, this is a similarity between UV spectra and Raman spectra. The radiation which we are going to use in Raman spectra is going to lie in UV range. Secondly, the range of Raman spectra is 1 centimeter inverse to 4000 centimeter inverse. So, in the last lecture, in case of IR spectra, the range of IR spectra was from 400 centimeter inverse to 4000 centimeter inverse. So, whole of the IR spectra, it lies within the Raman spectra. So, that is why we say that Raman and IR, they are complementary to each other. So, this is a similarity or dissimilarity between Raman and IR spectra, because they are complementary. So, they are similar as well as they have got some differences also. So, Raman spectra is given by, or the radiation which we use is, it belongs to UV spectra. The range of Raman spectra is 1 centimeter inverse to 4000 centimeters inverse, where whole of the IR spectra is going to lie within the Raman range. So, we say that Raman and IR, they are complementary to each other. Now, in Raman spectra, it is given by molecules will show change in polarizability. So, polarizability of the molecule, polarizability of molecule is the criteria for a molecule to give Raman spectra. Now, what is polarizability? We have got one more term which is a dipole moment. Now, polarizability is a relative tendency of charge separation. That is the meaning of polarizability, and polarizability normally takes place when an field is applied. Suppose we apply an electric field, then the polarization of charges is going to take place, and that is the meaning of polarizability. Dipole moment is charge separation. For example, if I take the molecule HCl, and this dipole moment is, for example, I am explaining dipole moment. So, for example, if I take HCl molecule, chlorine is more electronegative in comparison to hydrogen. So, this electron pair is shifted towards chlorine. So, chlorine acquires a partial positive charge and hydrogen acquires a partial chlorine acquires a partial negative charge and hydrogen acquires a partial positive charge. So this molecule is going to have a dipole moment. Why? Because of the presence of this electronegative group. But if I talk about H2, that is hydrogen and hydrogen, here both are hydrogen, so there is no electronegativity difference. So this molecule is not going to have a dipole moment. But to hydrogen molecule, if I apply an electric field, then the charge separation are going to take place. That means this molecule can be polarized, but it is not having a dipole moment. So dipole moment actually is the measure of polarizability. So in a hand they are same, but they are different. So polarizability is the relative tendency of charge separation, and if we talk about dipole moment, the dipole moment is measure of polarizability, and dipole moment is going to arise in the molecule when there is an electronegativity difference between the two atoms, for example in case of HCl. Now I told you that polarizability and dipole moment, so they are two things, but they have got some similarities also because the basis is same. So the Raman spectra is given by the molecules which can show polarizability, or polarizability of a molecule is the criteria for a molecule to give Raman spectra. So this is the basic of Raman spectra, that Raman spectra is given by the criteria for a molecule to give Raman spectra is polarizability of the molecule. Then Raman spectra, the radiation which we use belongs to UV range, and the range of UV spectra is 1 centimeter to 4000 centimeter inverse. Now in other spectras we were talking about radiations, we were using the word radiation like when the radiation is absorbed or radiation falls, but in case of Raman spectra we replace radiation by the word photon. So we will talk when a photon falls on a molecule, we can use radiation as well. Now suppose this is a molecule and a photon falls in it, or radiation, and this photon belongs to UV range. So when the photon is falling on the molecule, we can have two conditions. The first condition is the collision between, or the interaction between the radiation and molecule is elastic. When the radiation is elastic, that means the frequency of molecule and the frequency of photon is going to be same after the scattering. So when a radiation or a photon falls on the molecule, we can have two conditions. The first is elastic, second, suppose the second is inelastic. So that means when a photon is falling on a molecule, the scattering is taking place because in Raman spectra we are going to deal with the scattering. After the scattering we have two conditions, either the collision is elastic or the collision is inelastic. When the collision is elastic, in that case the frequency of the incident radiation and the frequency of the scattered radiation is going to remain same. So if this is the frequency, this is the frequency of scattered radiation or scattered photon, and this is the frequency of incident photon. So when the collision is elastic, in that case the two frequencies are going to remain same. This is not Raman scattering. Now when a radiation falls on the molecule and the collision is inelastic. Inelastic means the frequency of the scattered photon is either greater than or it is less than the frequency of the incident photon, and this is actually Raman scattering. So this inelastic collision is referred as Raman scattering. So this is what we have to study basically. So when a photon of some energy or some frequency falls on a molecule, we can have two types of collision. Either the collision is elastic or the collision is inelastic. When we say that the collision is elastic, that means the frequency of the incident photon is equal to the frequency of the scattered photon. And if we say that the collision is inelastic, this shows that the frequency of the incident photon is either greater than or it is less than the frequency of the scattered photon. Again, we can talk in terms of photon or we can talk in terms of radiation. So when the collision is inelastic, when the frequency of incident and scattered photon, they are different, it is either greater than or it is less than, that particular condition is known as Raman scattering. Now, if the kinetic energy after the collision or when the radiation falls on the molecule remains same, in that condition we write a term where h mu plus E is equal to h mu dash plus E dash. This can also be written as E minus E dash over h is equal to mu minus mu dash. So change in energy over h is equal to del mu. Delta E is equal to h del mu. So by this equation we are going to determine the energy when the photon is falling on the molecule and the kinetic energy is same before and after the collision. In that condition, the energy change in energy is given by h del mu. Now, so when a photon is falling on a molecule, we were having two conditions, one is elastic, the other is inelastic. To explain it by a graph, we can have, suppose this is one energy level, this is another, so 0, 1 and this is some other higher energy level n. So we have to draw three sets of this 0, 1 and n. This is 0, 1 and n. So I am drawing this to explain when the condition is elastic, when the condition is inelastic, and when the condition is inelastic, then how many possibilities are there. Suppose I am going to discuss the elastic condition where the frequency of the scattered radiation is same as the frequency of the scattered radiation. Here the molecule is moving from the ground state and it moves to some higher energy states, and anything which is moving in higher energy state cannot remain in the excited state for a very long time. It has to come back to the ground state. So when it comes back to the ground state, it is coming back to the same state from which it has moved. So this is known as, this is the condition of elastic collision, and this is known as Rayleigh scattering. This is Rayleigh scattering. So Rayleigh scattering means the molecule is moving from the ground state to some higher energy state, and then it is coming back to the same ground state. In this condition, the frequency of incident and scattered energy is going to remain same. In the second, we had inelastic condition where the frequency of incident radiation can be greater than or it can be less than the energy or the frequency of the scattered radiation. In that case, we can have two conditions, one where the energy is more and the other where the energy is less, or we can talk in terms of frequency. So in the second case, suppose the molecule is moving from the ground state and it is going to some higher energy state, but when it comes back, it is not coming back to the ground state, but it comes back to some higher energy state. This is first condition of inelastic collision, and this is known as stroke lines. The third condition is the molecule is moving from the ground from some higher energy state to upper energy state, and then when it comes down, it is not coming to higher energy state, but it comes back to the ground state. So this is the condition. This is known as anti-stroke lines. So these are the effects of when a photon of some frequency falls on a molecule. So when it is falling, we have two conditions, elastic and inelastic. This represent elastic condition and it is known as Rayleigh scattering. This is not Raman scattering. Now inelastic condition is considered as a Raman scattering. So both these, they come under Raman scattering. So Raman scattering, we have two conditions, either the frequency is greater, frequency of the incident radiation is greater than the frequency of scattered, or it is less than. To depict this, we have stroke lines and anti-stroke lines. In case of stroke lines, the electron is moving from the ground state, moving to higher energy state, but it is not coming back to the ground state, but it is coming to some higher energy state. But in anti-stroke lines, the molecule is moving from some higher energy state, it is moving up, but when it comes down to the ground state. Now if we compare the energies or intensity of these three, then this is of highest energy, then second is this, and third is this one. Why? Because in this case the molecules, in normal conditions, the molecules, they are normally present in the ground state. So if we talk about higher energy states, the number of molecules which are present in the higher energy states are less. So less molecules, when they are going to show transition, the intensity of the transition will be low. So in most of the time in Raman spectra, anti-stroke lines are not even visible. So in that case, we take concentrated solutions to carry out this Raman spectra. So if we talk about intensities, then anti-stroke lines, they have got least intensity, and the second is stroke lines, and first is Rayleigh's scattering. So once again, in Rayleigh's scattering is actually, it is not Raman scattering. Raman scattering is where we get strokes and anti-stroke lines, and strokes and anti-stroke lines are obtained when the collision is inelastic. So this is an introduction to Raman spectra. Now Raman spectra, whenever we carry out Raman spectra, it can be carried out it can be carried out in water, or that means we can use water, or we talk about aqueous solution. So water can be used as a solvent when we carry out Raman spectra. Secondly, because one of the Raman scattering, which is anti-stroke lines, is of very weak intensity. So to carry out Raman spectra, we require concentrated solution. So Raman spectra is always carried out in concentrated solutions. We cannot carry out Raman spectra in dilute solutions. And the main application of Raman spectra is used to study biological systems. For example, polypeptides and proteins. So with the help of Raman spectra, we are going to deal with some biological systems, for example, polypeptides and proteins. So this is the main introduction to Raman spectra. So Raman spectra is given by molecules which have got, or which show change in polarizability, or polarizability of the molecule is the criteria for a molecule to give Raman spectra. Then in Raman spectra, the light which is used, it belongs to UV range. Then the range of a Raman spectra is 1 centimeter to 4,000 centimeter inverse. Here whole of the IR spectra is present within Raman spectra. Therefore we say that Raman and IR, they are complementary to each other. Now, when a photon of some radiation or some frequency falls on a molecule, then we can have two conditions, either the condition is elastic or the condition is inelastic. When the condition is elastic, there we get Rayleigh scattering. It is not Raman scattering. But when the condition is inelastic, that refers to Raman scattering, where the frequency of the incident light is either greater than or it is less than the frequency of the incident light. And Raman scattering is of two types. Once we get stroke lines and the other we get. So, next is we are going to discuss rotational Raman spectra. Rotational Raman spectra. So, for rotational Raman spectra is given by the molecules which show change in polarizability. Now, in one revolution, the initial value of polarizability is attained twice. So, because of this, the selection rule in case of rotational Raman spectra is plus minus 2. Plus for stroke lines, minus for anti-stroke lines, and the equation is E is equal to Bj, j plus 1. This equation we have already derived in rotational spectra. So, if the transition is from j to j plus 2 and we put these values in this equation, we get energy is equal to B j plus 2 j plus 3 minus B j j plus 1. So, if we solve it, we get B j square plus 5j plus 6 minus j square minus j. So, it becomes B 4j plus 6. So, this is the equation in case of rotational Raman spectra. Now, if we draw the rotational Raman spectra, then suppose this is the lower energy level, which is 0, then 1, 2, 3, then we have the fourth energy level and the last fifth energy level. So, I am drawing a line to represent stroke and anti-stroke line within the same spectra. So, for delta j plus 1 we will have stroke lines, for delta j minus we are going to have anti-stroke lines. So, the transition is going to follow delta j is equal to plus minus 2. So, the transition will be from 0 to 2, 1 to 3, then 2 to 4 and 3 to 5. So, they correspond to delta j is equal to plus 2 and plus 2 corresponds to strokes lines. Similarly, we are going to have for negative sign, for negative because that is going to show emission. So, it will be drawn downwards. Everything will be same, but this will be drawn downwards. So, this is delta j is equal to minus 2, which is going to represent anti-stroke lines. So, this is rotational Raman spectra. Then we consider the vibrational Raman spectra. So, in vibrational Raman spectra, we are not going to discuss it in detail. So, next is vibrational Raman spectra. In case of vibrational Raman spectra, the selection rule is delta V plus minus 1. So, plus is for stroke lines and minus is for anti-stroke lines. So, this is considered in vibrational Raman spectra. At the last, we are going to consider rotational and vibrational Raman spectra or vibrational rotational Raman spectra. So, at the end, last is vibrational rotational spectra in case of Raman. Now, here for vibrational, the selection rule is delta V plus minus 1. So, the selection rule here is delta V plus minus 1, and the selection rule for rotational is going to remain same, delta J plus minus 2. So, in this spectra we are also going to show Rayleigh scattering, which is elastic collision, elastic condition. So, to draw the vibrational rotational spectra, suppose this is V and the transition is to V plus 1. This is vibrational changes. So, it is undergoing plus and the transition is plus minus 1, and within vibrational energy level we have got rotational energy levels. So, to draw rotational energy levels, these are the rotational energy level. This is 0, this is 1, then 2, it is longer, then we have 3, then 4, and then we have 5. These are rotational energy levels. Rotational energy levels for V is for vibrational state V. So, this is 0, 1, 2, 3, 4, 5, and for rotational energy levels for V plus 1, this is 0, then we have 1, this is 2, 3, 4 and 5. So, this is 0, 1, 2, 3, 4 and 5. So, within vibrational energy levels we are having rotational energy levels. Now, we are going to see transitions, and transitions will be of 3 types. One, we are going to consider Rayleigh scattering, then stroke lines, and the next we are going to consider anti-stroke lines. So, we are discussing at present rotational vibrational spectra. The selection rule for vibration is plus minus 1 and the selection rule for rotation is plus minus 2. So, first we are going to draw Rayleigh scattering. So, to draw Rayleigh scattering means the transition will take place from 0 to 0, then 1 to 1, and the lines of transition Rayleigh scattering were very close by, they are close to each other, 2 to 2, then 3 to 3, 4 to 4, and then 5 to 5. Now, this corresponds to delta J is equal to 0 and it is Rayleigh scattering. This is Rayleigh scattering, and one thing you have to remember is these lines should be close by, it should not be far from each other. Next we draw anti-stroke lines, stroke lines. So, stroke lines are positive. So, lower energy level to higher energy level. So, the transition is going to take place from 0 to 2, then 1 to 3, then 3 to 4, and last is 4 to. This is the transition, this is 2 here and this is the condition. So, these are all delta J plus 2. So, delta J plus 2, these lines they represent stroke lines. Then we represent anti-stroke. Anti-stroke means higher energy to lower energy. So, it starts from 2 and it ends up at 0. Then 1 to 3 to, it will go to 1. Then 4 to 2 and then 5 to 3. These are the lines which are delta J is equal to minus 2. So these are anti-stroke lines, this is stroke lines, and this we are having Rayleigh scattering. So this is the rotational, vibrational rotational spectra in case of Raman. Here the selection rule for rotation is delta J plus minus 2 and the selection rule for vibration is plus minus 1. These lines in the middle, they show Rayleigh scattering, which is elastic collision. In this side we are having stroke lines, on the other side we are having anti-stroke lines. So these are spectra in Raman. So initially we considered rotational spectra in Raman, then we considered vibrational spectra in Raman, and in the last we considered rotational vibrational spectra in Raman. Now in the starting of the lecture I told you that IR spectra and Raman spectra, they are complementary to each other. Why? Because the Raman spectra, the range is 1 centimeter to 4000 centimeter inverse. This is the range of Raman spectra. In case of IR, this range is 400 centimeter inverse to 4000 centimeter inverse. This is the range of IR spectra. So whole of the IR spectra lies within the Raman spectra, and we say that Raman and IR are complementary to each other. So if we discuss the difference between Raman and IR, then this is Raman spectra and we have IR spectra. Now Raman spectra, it deals with scattering of light. Scattering of light. Whereas IR spectra deals with absorption of light. Absorption of light is going to take place in IR spectra. In Raman spectra, the radiation which is used belongs to UV range. So in Raman spectra, we require ultraviolet radiation, whereas in IR spectra, as the name suggests, we require infrared radiations. Now Raman spectra, here water can be used as a solvent. So whenever we carry out the Raman spectra, we can use water as a solvent. So water is used as a solvent. Whereas whenever we carry out IR spectra, it is never carried out in water. So water cannot be used as a solvent. So this is the main difference. Then I told you that Raman scattering is of two types, strokes and anti-stroke lines. And anti-stroke lines, the intensity of anti-stroke lines is very weak. And in general also Raman spectra is not very strong. So to carry out Raman spectra, we require concentrated solutions. Raman spectra cannot be carried out in dilute solution. So the solutions which we require here are concentrated solutions. This spectra cannot be carried out in dilute solutions, whereas the IR spectra, it can be carried out in dilute solutions. So and Raman spectra is the basis of Raman spectra is the change in polarizability, whereas in IR spectra, the basis of IR spectra is the molecule should have permanent dipole moment, which should change when the molecule undergoes vibration. So that is a difference. And if we talk in terms of dipole moment and polarizability, then here the requirement is polarizability and here the requirement is dipole moment. And dipole moment is the measure of polarizability. So a molecule may not have dipole moment, but it will have polarizability. That is known as role of mutual exclusion. So to discuss the role of mutual exclusion, suppose I take up hydrogen and I take up water, or hydrogen or Cl2 molecules. Now these two molecules, this molecule is IR inactive because this molecule is not going to have dipole moment. Why it is not having dipole moment? Because for dipole moment, the two atoms, between two atoms, the electronegativity difference should be there. Whether we consider hydrogen or we consider chlorine, they have got same electronegativity, so they cannot have dipole moment. But if I place an electric field either to hydrogen or to chlorine molecule, then there will be a change in polarizability. So H2 or Cl2, they are homonuclear molecules. They are not going to give IR spectra, but they are going to give Raman spectra. Why? Because whenever they come in influence of an electric field, there will be a change in polarizability. If we take up hydrogen molecule, water is IR as well as Raman active. So IR, it is going to give IR spectra. It is also going to give Raman spectra. Now, if we can consider one more example, which is this one. Hydrogen, Cl and Cl. This is a trans isomer, and we draw the cis one. Now, this is the cis form. If we see the first one, we encounter same molecule. That means this molecule is having a center of symmetry. So, and any molecule, if it is having center of symmetry, that means that molecule will be IR inactive. So if we see out these two molecules, this molecule is IR inactive. Why? Because it is having center of symmetry. It is Raman active as well. Both the molecules are Raman active, but this molecule is IR inactive. But if we come here, this is not having center of symmetry. This molecule is going to give IR spectra as well as it is also going to give Raman spectra. So we say that IR and Raman, they are complementary to each other. Now with the help of Raman and IR spectra, we can also determine the structure of any molecule. Suppose I have got this molecule CS2 and N2O, and I say, or I know that the first molecule is IR inactive and it is Raman active, whereas if I know that the second molecule is IR as well as Raman active, so by this piece of information that this molecule is IR inactive and Raman active, and this is IR as well as Raman active, I can conclude straight that this molecule is having a center of symmetry, and because it is having a center of symmetry, so it is IR inactive. So the structure of this is carbon, sulfur and sulfur. Now, with this piece of information, I can tell the structure of this molecule that this is not going to have any center of symmetry or any kind of symmetry. So, the structure will be N, N and O. So, if we know what is the condition or what are the whether the molecule is IR active or Raman active or both active, we can determine the structure of the molecule. So, in Raman spectra, the important things are, it is given by the radiation which we use belongs to UV range. Then the range is 1 centimeter to 4000 centimeter inverse, and it is given by molecules which show change in polarizability. This is the condition. And Raman scattering means we are going to get stroke lines and we are going to get anti-stroke lines. Stroke lines, they are of higher intensity in comparison to anti-stroke lines, and the basic application of Raman spectra is given by, or it is important in biological systems. For example, if we have to study polypeptides or proteins, then we use Raman spectra. And Raman and IR, they are complementary to each other. With the help of Raman and IR spectra, we can determine the structure. We can determine the structure of the molecule. If the molecule is having any kind of center of symmetry, that molecule is IR inactive. So, if we have to discuss all the 4 spectra which we have studied in unit 2 one by one with the difference and with the similarity, just brushing up of all the spectra. The first spectra we dealt was UV spectra. UV spectra, as the name suggests, we require ultraviolet radiation. The range of UV spectra is 200 nanometers to 340 nanometers, and it is given by the molecules which have got unsaturation. Unsaturation with conjugation, and greater the conjugation, greater is the wavelength for absorption. This is the basis of UV spectra. The second was rotational spectra. Rotational spectra, the range is 1 centimeter to 100 centimeter inverse. The radiation which we used in rotational spectra belonged to microwave range. And rotational spectra is given by the molecules which show permanent dipole moment. And in microwave or rotational spectra, we restrict our study to diatomic molecules. Why? Because if we go for higher molecules like tri or tetra, then the derivations and the expressions, they become very tedious. We cannot calculate it. It becomes a chaos there. So we restrict our study in rotational spectra to diatomic molecules. If we come to IR spectra, the range of IR spectra is 400 centimeter inverse to 4000 centimeter inverse. And IR spectra, as the name suggests, the radiation which we use are infrared radiation. And IR spectra is given by molecules which have got permanent dipole moment, which changes when the molecule undergoes vibration. So here if you can see, rotational spectra and IR spectra, in both the cases the molecule should have a permanent dipole moment. The difference is, in case of rotational spectra, that dipole moment is not going to change when the molecule is rotating, but in case of IR spectra, when we have vibrational changes, then the dipole moment should change when the molecule undergoes vibrations. And the last spectra we discussed today is Raman spectra. Raman spectra is one difference out of these 4 is in the first 3 spectra they deal with absorption of radiation, whereas in Raman spectra we deal with scattering of radiation. Now the similarity between UV and Raman is the radiation which we use here belongs to UV range. Then the range of Raman spectra is 1 centimeter inverse to 4000 centimeter inverse. So this is the similarity here between IR and UV. The whole of the IR range is present within the Raman spectra. So and that is why we say that IR and Raman are complementary to each other. So these are the 4 spectras which we have discussed in spectroscopy. So this is all in this unit. Thank you.